So, good morning all. So now we are going to discuss about our final conversion, which is called as your T flip-flop conversions. So already we know that what is called as a T flip-flop. So T flip-flop, T stands for your toggle flip-flop. Okay, toggle flip-flop. So now this T flip-flop I am going to convert into D flip-flop, SR flip-flop and JK flip-flops. Clear? Now we are going to convert this D into T, SR and JK. So first thing we want to know which is the source and which is the destination. So here T is here source flip-flop and D or SR or JK are nothing but here destination flip-flops. And as per our conversion concept, always for the destination flip-flop we want to go with the extended truth table. So for this we want to go with the extended truth table, and for this I will be going with our excitation table. I will be going with our excitation table. I will be going with my excitation table. Okay, so we want to know what is the excitation table for our T flip-flops. Okay, so the excitation table for the T flip-flop, already when we are discussing about the generic expressions, we have seen the excitation table for the T flip-flops. So once again we can recall what is the excitation table for our T flip-flop. Okay, so when you talk about this T flip-flop, the excitation table, if you see, this is the excitation table for my T flip-flop. Okay, so 0 0 means 0, 0 1 means 1, 1 0 means 1, 1 1 means 0, that is 0 1 1 0. So this is the excitation table. So this one you want to keep it in the mind while you are implementing or while you are doing the conversions for this particular type of T flip-flop. Okay, so first thing is you are going with your D to D flip-flop. So for the D flip-flop I am going to draw the extended truth table. So D and Qn and Qn plus 1. Okay, Qn plus 1. So Qn can be either 0 or 1 for the input 0, and Qn can be either 0 or 1 for the input 1. And D flip-flop means it is a direct thing. For the input is 0, output will be 0, and input is 1, the next state will be 1. So now we have drawn the destination flip-flop extended truth table. Now I want to draw the excitation table with respect to this extended excitation table. So before that I am going to write the excitation table for your source. Source is nothing but here which source is T flip-flop. So T flip-flop excitation table I am going to write. So which is going to depend on Qn plus 1 and what is the mandatory input. So it may be either 0 0, 0 1, 1 0 or 1 1. And already we have now only seen it is nothing but 0 1 1 0 concept. So apply this over here. So if the inputs are, that is present state and the next state are 0 and 0, my mandatory input is 0. If it is 1 0, it will be 1. For 0 1 also it will be 1. For 1 1 it will be 0. Clear? For 1 1 it is on the 0. Now this stands for here extended and truth table of destination, which means that here D flip-flop. Okay, and this stands for here excitation for source, that is here T flip-flop. Okay, now based on this we are going to draw the K map reduction for source. K map reduction for source, that is here T flip-flop, where you got your output as 1. So it is nothing but a 2 variable function. So I am going to draw a 2 variable. One input is on the D, other input is Qn. It can be either 0 or 1. This can be also either 0 or 1. So if the input is 0 and the present state is 1, my output is becoming 1. Input is 0 and the present state is 1, my output is becoming 1. And input is 1 and the present state is 0. Input is 1 and the present state is 0. 1, 0, my output is becoming 1. Okay, so this is nothing but what? So one single, this one single. So and this is nothing but D bar, nothing but D bar into Qn, and this is nothing but D into Qn bar. Okay, D into Qn bar. So your T is nothing but D into Qn bar plus D bar into Qn. Now for the now we are going to convert our T to D. So T is the main thing. We are converting this into D flip-flops. So which will be having one present state and the complement of the present state, and there will be one clock pulse. Okay, and D and D bar we want to have. So D and D bar we will take. So this is here on the D. So another NOT gate, I will get your output as here D bar. Okay, D bar. So two things we have taken. So from the D, okay, so from here we will take. Okay, from here one input is on the D. Okay, another input is here Qn bar. Okay, so one input is D, another input is Qn bar, and similarly for here one input is D bar, another input is Qn, another input is Qn. So both the things, now we are making one OR gate. Okay, and this is connected to your T input. Okay, so this is connected to your T input. Now I have converted my T flip-flop to D flip-flop. I have converted my T flip-flop to D flip-flop because I am giving the input as on the D. It is going to produce my output. So now T is converted into D. Clear? So now we will go for the next type of the conversion, and which is called as T flip-flop to SR flip-flop. Okay, toggle flip-flop, that is T flip-flop to SR flip-flop. Okay, so here if you see, SR is here a destination flip-flop and T is here source flip-flop. So for this destination you want to write here extended truth table, and for this you want to write here, for the source you want to write here excitation table. Okay, so first for the source I will write here excitation table, that is for the T flip-flop I will write my excitation table. So if you see the excitation table for the T flip-flop, it is Qn plus 1, and what will be the mandatory input of T? May either 0 0, 0 1, 1 0 or 1 1. Okay, and it can be either 0 1 1 0. So this is the excitation table. Now for the destination table SR flip-flop I am going to draw here extended truth table. Okay, extended truth table. So your SR can be either 0 0 with the in present state as 0 1, and it can be either 0 1 with your present state as 0 or 1, and it can be either 1 0 with your present state as 0 1, and it can be either 1 1 with your present state as 0 0. Okay, so now we want to write the so now we will be writing the extended truth table for this. Okay, you will be writing the extended truth table for this. So if you write the extended truth table, this will be like the present state will be retained as such. For 0 0, for 0 1 it will be 0, for 1 0 it will be 1, for 1 1 it is like a indeterminate form, so we cannot determine anything. Now based on that I am going to extend this to the T flip-flop. Okay, so extending using the excitation table. So if it is 0 0 it should be 0, if it is on the 0 0 it should be 0, and if it is 0 1 it is 0 1 it should be 1, if it is 0 1 it should be 1. Okay, it is 0 1 means it should be 1, and for 1 0 it should be 1, for 1 0 also it should be 1, for 1 1 it should be 0. Okay, so 1 1 it should be 0. So totally we have around for 0 0 condition, 1 1 condition. Yeah, okay, done. So these two things we are not going to consider. Now we are going to draw the T. Okay, so for the T for the T we are going to draw the K map reduction. Going to draw the K map reduction. So you see K map reduction. So one of the input is, so one of the input is what? S and R, another input is Qn. So Qn, S and R, 0 0 0 1 1 1 and 1 0 0 1. So now if you see, there are only for the two things we got here output as 1 and 1. So that is for 0 1 combination with 0 1 and Qn as 1, 0 1 and Qn as 1, and next thing is 1 0 and Qn as 0, 1 0 and Qn as 0. Okay, 1 0 and Qn as 0. Now we got the output. Since for 0 0 it is 0, for 0 1 for 0 1 for 0 1 it is 1, and 1 0 it is also 1. Okay, so So now this is something. So this is nothing but s into r dash, s into r dash into qn dash, and this will be something like s dash into r into qn. Okay, s dash r into qn. If I segregate this, what will be your answer? 0 1. So for this, for 000 I will get the output as on the 0. For 0 1, for 0 1 I will get here, for 0 1 I will get my, for 0 1 I will get my output as 1. Similarly here also 0 1. So 1 0 I will get your output as on the 1, and for 1 1 my output will be 0. Okay, so you will be having 1 0 0. So if you see it is 1 0 0, either you cannot on the provide whether it is 1 or on the 0, so we cannot tell the term. So 1 so 1 0 and 1 1 0, 1 1 0 if I make, okay, 1 1 0, which is 1 1 1 and 0, it can be either on the x condition. Similarly 1 1 1 1 and 1, this also may be on the x condition. If you got a system like this, okay, that is in the don't care condition, your expression will be further reduced. So this will become, so I will highlight this using a blue color. So there may be a possibility I am telling, but it is not a mandatory thing. If you group like this, this will be something like your q dash n into s, and this will be something like qn into r, okay, qn into r, since we are having a combination for the next set like this. Okay, next set like this. So when I am going with this type, okay, when I am going like this type, you will be having your T flip-flop as here on the source, and you have your clock. Okay, இது வந்து qn, and this will be your qn bar, and you have my, this is nothing but for your t map and the reduction. So t equal to s into qn dash plus r into qn. Okay, s into qn dash plus r into qn. I think it is taking some time. Okay, no problem. So I'm going to connect. So okay, so this is for here s into qn dash, and this is for here r into qn. And qn. So first thing is what, s into qn dash, no, s into qn dash. So this one I am going to connect with here qn dash, and next thing is r into qn. So this is here on the r into qn, r into qn. So the output we are going to connect to here t variable. So this is how we are converting our t flip-flop to SR flip-flop. So t flip-flop is now converted into SR flip-flop. So we will be having an S input, R input, and now we are converting our t flip-flop to SR flip-flop. Now we will go to the next conversion, which is nothing but our t flip-flop to JK flip-flop conversion. Okay, so here also first thing is, the main thing is, it is nothing but here destination flip-flop, that is JK is here destination flip-flop, T is here source flip-flops. So for the destination flip-flop, I want to draw my extended truth table. Okay, and for the source flip-flop, we want to draw here excitation table. So for the source flip-flop, that is for the T flip-flop, as usual I am drawing my excitation table, so which will be depend on present state and the next state, and what will be my T input, maybe either 0 0 0 1 1 0 and 1 1 and 1 0 and 1 1. So it may be 0 double 1 0 0 double 1 0. This is their excitation table. And JK flip-flop destination. For the destination, you want to draw the extended truth table. Extended truth table you want to draw for the JK flip-flop. So JK QN plus 1, and that is QN. Then is here QN plus 1. Extended truth table I am going to draw. So 0 0 0 1 0 0. Whether the present state may be either 0 or 1, and next thing is for 0 1 condition also present state can be either 0 or 1. Okay, 0 or 1. And next thing is for 1 0 condition also present state can be either 0 or 1, and for 1 1 condition also present state can be either 0 or 1. Okay, so here you want to check it. If it is JK 0 0, there is no change. For 0 1 it is on the 0. For 1 0 it is on the 1. For 1 1 the present state is getting complemented to 0 as 1 and 1 as 0. Now I am going to draw the extended truth table, that is excitation table with respect to T. So what is the excitation table? If it is 0 0, it should be equivalent to 0. 0 0 means it should be equivalent to 0, and 0 1 means it is 1. Where you got 0 1? Here I am getting on the 0 1, and here also I am getting a 0 1, and 1 0 it is 1, 1 0 it is 1, 1 0 it is 1, and for 1 1 it is 0, 1 1 it is 0. Clear? So 1 1 it is 0. Now what you are going to do? Now I am going to draw the some Carnot production for this T input. So T input Carnot production. Carnot production. Okay, so it is going to depend on 3 variables. The inputs are nothing but JK, and another is on the QN. The QN 0 0 0 1 1 1 and 1 0. 1 0 be either 0 or 1. So you want to check where you got here output as 1. So in the 4 condition we got my output as 1, that is 0 1 1 0 1 1 0 1 1. I got my output as 1. Next one is 1 0 and 0. 1 0 0, got my output as 1. The next one 1 1 0. 1 1 0, I got my output as 1. 1 1 1, I got my output as 0. Okay, so 1 1 1. So if you see, this will be one pair and this will be another pair, and for this pair the answer will be J into Qn bar, and for this pair the answer will be K into Qn. K into Qn. So this is nothing but my equation, that is T equal to J into Qn bar plus K into Qn. clear? So now you are going to convert your T flip-flop to JK flip-flop. So T is my input, and here you will have your Qn, and under is here on the Qn bar, and here there will be a clock pulse, okay, J into Qn bar. So here I will be having one AND gate, and here another one AND gate, and both are connected to one OR gate, okay, both are connected to one OR gate. So here one of the input is on the J, another input is Qn bar, and similarly here one of the input is on the K, another input is Qn, clear? So here if you see, now we have converted the given T flip-flop to JK flip-flop, where I will be giving the input in the terms of JK, and I am getting here outputs as Qn plus 1 and Qn plus 1 in the whole bar. So here you will get your next state as Qn plus 1, the next state will be Qn plus 1 the whole bar, okay. So now we have done for all the three conversions. So now we have seen the conversion from here T, that is toggle flip-flop, to all the three types. That is, we have converted into D flip-flop, we have converted into SR flip-flop, and we have converted into JK flip-flop. So all the three flip-flop conversion has been completed, and moreover we have converted all the 12 on the conversions has been completed. So those who have missed any one type of on the conversion of any, that is either D to T or SR to T or JK to SR or SR to D, so all the conversion has been available in our previous videos, and I request you to complete or check and ensure that you have only completed every videos, okay. So thank you all once again for your patient listening these videos, okay. So we will see in the next lecture about the multiplexer practical implementation, okay. So how we will convert a multiplexer implementation point of view, that is how to implement your mux, okay. That is either how we can implement a 4x1 mux in terms of 2x1 mux, or we will implement an 8x1 mux in terms of 4x1 mux, or we can see how to implement an 8x1 mux in terms of 2x1 on the mux, and so on. So all this on the implementation we will be seeing in the next video, and thank you, and once again all happy studying.